Let's do some problems. So specifically on tensor products of vector spaces. Okay, so recall vector spaces are nothing but modules over a field F. So let's fix a field F. So field is necessarily a commutative ring. So recall we have an alternate universal property for the tensor product in this case. So what was the tensor product? If I give you two vector spaces V and W, then both vector spaces over F, vector spaces over the field F, the tensor product V tensor W over F has the following universal property. You can define it as the object which has this universal property, which is that given any bilinear map, any F bilinear map from V cross W to any other to any F vector space Z, okay, given any F bilinear map F where Z is again so take Z again to be a F vector space, then this map gives rise to a unique F linear map. Okay, so this is now an F linear map. The original guy was F bilinear. And this map here now is just a standard map which just takes every pair V comma W and maps it to the corresponding element of the tensor product, okay, what we called alpha before. Okay, good. So that's just a recall of what the tensor product was. So observe, so as an example, so let's do maybe problem 1. So let's take just the vector space F itself, a one-dimensional vector space over itself. Now I claim that if I look at F tensor F over F, then this is just isomorphic to F. Okay, so let's this is an instance of a general thing we have proved before, but let's anyway prove this from scratch. So I have to try and construct a map from F tensor F to F. So the correct way to start is to first construct a bilinear map from F cross F to F. And this is easy. If you just take a pair of elements A and B in F, I can just define their product AB in F. And observe the product map is of course bilinear. Okay, so observe that this is clearly F bilinear. Okay, it's easy to see because of the distributivity property in the field. Now what that means is that this gives rise to a unique map from F tensor F over F to F. Okay, so there is a unique map F tilde, and this map, well, what does this map do? It takes the element A tensor B of F and gives you the element AB. Right? This is because it makes this diagram commute. So observe on the generators, on the elements A tensor B, this just gives you the product AB. Okay. Now the claim is that this map F tilde is actually an isomorphism. F tilde is an isomorphism of F vector spaces. Okay, it's easy to see that it's onto, so that's the easy part. F tilde is onto because every element of the field can just be obtained as the image of this special element. Just look at one tensor B, that's just an element B. Okay, so I can just take just let B run over all possible elements of F, and the image of the element 1 tensor B is exactly B. Okay, now why is this 1-to-1 F tilde? I claim is also a 1-to-1 map or injective map. And to prove this, let's consider a typical element. So let's take an element xi equals summation ai tensor bi in F. So this can also be written as, so I assume that xi is in the kernel of this map. Okay, and my goal is to prove that xi is 0. So xi can also be rewritten as, well, I can push the ai over to the other side. Okay, if you wish, this is the R balanced condition. So right, you can push it from one side to the other. So I'm thinking of the ai in the first component as 1 times ai. Okay, and now I use the fact that this symbol is bilinear. I can write it like this. Okay, and what's f tilde of this? Therefore, f tilde of xi is of course by definition summation ai bi. Okay, and that's given to be 0. So I've assumed that xi is in the kernel. So what does that mean? It means summation ai bi is 0, but then xi is of the form 1 tensor 0, right? Therefore, what it means is xi is just 1 tensor 0, and this we have proved before, that anything tensor 0, that element is always the 0 element of the module by just writing 0 as 0 plus 0 and so on. Okay, so I won't repeat that argument. Observe that xi essentially becomes 1 tensor 0, and therefore that's just the 0 element. So that shows that the kernel of this map is just trivial. In other words, the map is 1 to 1. Okay, good. So that completes the first example. F tensor F is actually just F. Okay, now more generally, what if you took vector spaces of other dimensions? Let's say finite dimensional vector spaces. So let's say F is a finite dimensional. So let's even say it has some dimension of V is a vector space of dimension n, W is a vector space of dimension m. So all vector spaces over the field F. Then claim is that V tensor W is in fact a finite dimensional vector space whose dimension is just the product of the two dimensions. Okay, so you had seen this back in Algebra-I as well, but let's redo this from our point of view. Now, in fact, more is true. In fact, if you just take a basis, if Vi is a basis of V and Wj is a basis of W, then we claim that the elements Vi tensor Wj, these nm elements 1 less than equal to I less than equal to n, they form a basis of V tensor W. Okay, and that will of course show that the dimension is nm. So let's prove this stronger fact that these guys form a basis. So observe firstly that they certainly span. Okay, why do they span? So observe that elements of the form just a single V tensor, a single W, right? What we call the simple or decomposable tensors, elements of this form certainly span V tensor W. Okay, so recall this fact. So this just came from more or less the construction of the tensor product. So these fellows definitely span over F, if you wish. They span this space over the field F. Now, any such element can be rewritten as follows. If I write V as a linear combination of the Vi's and W as a linear combination of the Wj's, then by the bilinearity of this tensor symbol, V tensor W will just become summation ai bj Vi tensor Wj. Okay, now this is now I going from 1 to n, j going from 1 to n. So what this means is that these elements Vi tensor Wj, they certainly span the space, because V tensor W's are all expressible as a linear combination of the Vi tensor Wj's, and V tensor W's, when you change V and W, they span the space. Okay, so this certainly means, so let's just give this space, set a name, script B. B certainly spans the vector space V tensor W over F. Okay, now we just need to show that B is linearly independent. So let's show linear independence of B. So what that means is you need to take a linear combination Cij Vi tensor Wj. So this over all i's and j's running over the appropriate indices. Suppose this is 0. Okay, now what is this? This is an element of V tensor W. So I'm saying, suppose as an element of V tensor W, this sum is 0, then I need to show that this element itself is I'm sorry, I have to show that all the Cij's are 0, right? So I need to show that Cij is 0 for all I and for all j. Okay. Now, to do this requires something a little bit more. Okay, we need to work slightly harder. So observe that when I have bases vi and wj of my vector space, I also have what are called dual bases. Okay, so let's give those also names. Let fi belong to v star. This is for I from 1 to n, and gj belonging to w star be the dual bases, okay, corresponding to the v's and the w's respectively. Okay, now what does dual basis mean? Recall that these dual basis elements are just the following. When I evaluate fi on a given vk, then it gives me 1 if k is I and gives me 0 otherwise. Similarly, if I evaluate gj on wk, it will only give me 1 if k is j otherwise. Okay, so these are what you call the dual bases. Now observe that fi and gj are linear functionals on v. So in fact, what that means is that I can think of it as follows. It's a map from v to f. Right? This is what fi is. gj is a map from w to f. Okay, so now let's use something that we learned about tensor products, that this tensor is really a functor. In other words, not only does this give me a map, not only am I constructing an object called the tensor product of two vector spaces, if I have maps between the components from v to a vector space and w to a vector space, then it induces a unique map from v tensor w to the tensor product of those two vector spaces. So if I take this map here, this is fi, what we called as fi tensor gj. Okay, so this is a map from v tensor w over f to f tensor w over f. Okay, now what does this map do? Recall, it takes a simple tensor of the form v tensor w and maps it to fi of v tensor gj of w. Okay, but now recall, we have just now done this. The previous problem says that f tensor f is actually just f. Okay, and what was that map? It was just a product map. So this is fi of v into gj of w. Okay, good. Now what does this mean? It says that I have a map from v tensor w to f, which just takes v tensor w and maps it to fiv times gjw. Okay, good. So this is a well-defined, there exists a well-defined map. So maybe we should just call this composition as something. Maybe I'll call it phi sub ij. Okay. Okay, so phi ij is therefore a linear functional, if you wish. So what is phi ij? It is a linear map, f linear map from v tensor w to f. In other words, it's an element of the dual space. So what we have constructed is an element of v tensor w star. Okay, good. Now why is that useful? Because this is what we were trying to prove. We are given summation Cij wi tensor vi tensor wj is 0, and from this we need to somehow show that all theCij's are 0, right? So now let's do that. So given this, so maybe we should just change these indices for the moment. So let's just call it ckl vk tensor wl. So the sum is over all k going from 1 to n, all l going from 1 to n. Now what we do is we'll apply this special element phi ij that we just constructed to both sides of this equation. Okay, now what does phi ij do? Well, when it acts on vk tensor wl, look back on what it did, it's just fi of vk multiplied by gj on wl. Okay, and since f and g are just the dual bases, this will give you 1 or 0. This gives you 1 precisely when k equals I and L equals j and will give you 0 in all other cases for all other pairs. Okay, good. So what does that mean? Which implies when I apply phi ij to the left hand side, phi ij of the left hand side of this equation here, all the terms are going to become 0, okay, except a single term which corresponds to Vi tensor Wj. Okay, in other words, I will just get Cij as my answer. And of course, the right hand side, phi ij of the right hand side is 0. Okay, so what I have done is shown that phi ij of the LHS, which is Cij, is 0, and this is true for all I and all j. I can just change my I and j, and so I am done. That's exactly what I wanted to prove. Okay, good. Okay, let's go on to the next problem. Now, suppose I have the same hypothesis that V and W are finite dimensional vector spaces. Let's say this is dimension n and this is dimension m. Then I claim that there is a certain natural isomorphism between the following two vector spaces, from V star tensor W to the space of all linear transformations, okay, what I'll call as Hom F linear maps from V to W. Then there exists a certain map, then so let's call it psi, then the map psi, which I will define in a moment, is an isomorphism. That's a claim. Okay, so what is the map itself? Well, the map is the following. So firstly, there exists a map as follows, which is, so firstly, maybe we should start one step earlier, which is we should first try to construct some bilinear maps. So let me give you an example of a bilinear map from V star cross W to the space of all homomorphisms. So V star, recall, is the dual space. Those are the linear functionals, and W is just elements of W. Corresponding to this pair, I will associate a certain linear transformation. Okay. Now, what is this linear transformation? If I take T corresponding to the pair FW, when I evaluate it on a vector V, okay, my definition is the following. I can evaluate F on V, that will give me a number, and then I can multiply the answer by W. So this answer now is in W. So observe that this definition is, well, firstly the output is certainly an element of W. This is a linear transformation because when I change W linearly, when I change V linearly, when I make it V1 plus V2 or some scalar multiple of V, then since F is linear, this splits either as F of V1 plus V2 or as lambda times Fv. Okay, so this is in fact this is definitely F linear because this linear functional F is after all F linear. Okay, good. Now, therefore, I've certainly defined an operator in or a linear transformation in Hom F VW. And in fact, if you think about it a little bit, you will see that what sort of operator have we defined, or what sort of transformation? This is something which is of rank 1. Okay, this is a rank 1 transformation, which the range of this transformation is exactly 1. Okay, or if maybe this linear function is 0, then it could just be the 0 operator. So to be very precise, we should say, well, what sort of thing are we doing here? Corresponding to a linear functional F and a vector W, we are associating a rank at most 1 linear transformation. Okay, good. Now observe that this map is bilinear. Okay, so this association that I have here, so maybe we'll call this psi tilde and call this bilinear map as psi. So the other thing is that psi itself is bilinear, is F bilinear. Okay, i.e. what should we check? If I change F to F1 plus F2 and keep W the same, then what I get on the other side is a sum of the answers. Okay, so in other words, T, so I should have done this, T of F sub the ordered pair FW. So I claim that the operator T F1 plus F2W is just the sum of the operators T F1W plus T F2W. Okay, and similarly, for scaling and so on. So if I multiply this by some scalar, t of lambda fw is just lambda t of fw. Okay, and I should do the same thing in the other component, which is t. I keep f constant. I write this as w1 plus w2. Then this just becomes t fw1 plus t fw2. And finally, the last thing, if I change this to a lambda, then the lambda comes out. Okay, so I'm going to leave all these 4 verifications as an exercise. It's just a straightforward application of the definitions. So what this means for us is that you have this nice way of combining a map like this, okay, which is an element of v star cross w. I mean, you have given a linear functional and a vector. There's a nice way of constructing in a bilinear fashion a rank 1 transformation. Okay, good, but the important thing is that this is bilinear. Okay, now what does that tell us? It tells us by the universal property that I have a map from v star cross w, which I called psi, to the space of homomorphisms, and now by the universal property I know that there exists a map, a unique map psi tilde, which makes this diagram commute. Okay, so there exists a unique f linear map psi tilde such that psi tilde on what? On f tensor w is the operator tfw that we associated. Okay, now the claim is that this map is an isomorphism. So that's my point finally. The map psi tilde defined in this way is in fact an isomorphism of vector spaces. Okay, so observe that firstly it's an onto map. That's again the easy part of the proof. Observe that psi tilde is definitely onto. Okay, why is it onto? Well, because what should you show? To show that it is onto, you have to take an arbitrary linear transformation here, take some random linear transformation and show that you can obtain that in the image of psi tilde. Okay, now psi tilde is this is what psi tilde does, right? Now how do I obtain any linear operator as the image of something in psi tilde? So the point is, this is only the action of psi tilde on the decomposable tensors, remember. So more generally, if I write it as a summation, then it will become the corresponding sum. So psi tilde on a sum of the following form, fi tensor wi is therefore the sum of t of fi wi. Okay, and that's the key. Okay. Now the point is, any linear operator, linear transformation can always be written as a sum of rank 1 transformations. Okay, so let's just see why that's true. So given any t, so what does t look like? T acts on v, it gives you some vector in w, and let's fix a basis of w. Let's fix a basis like we did before. Fix a basis of w. So then, since tv is a vector in w, I can write it as some unique linear combination, in fact summation ci wi. Okay, but of course these ci's, these scalars depend on v. So I'll indicate it like this: the constant ci, the linear combination, the scalars occurring there depend on v, and ci of v, observe. So t, the key fact now is the following: t is linear implies that the ci's are actually linear functionals. They are also linear operators. In fact, it's an if and only if statement, right? So if t is a linear transformation from v to w, then it means that these coefficients are all linear functionals. Okay, again easy exercise, just linearity of t translates into linearity of the ci's. Okay, good. So what does that mean? Then that just tells you that by definition T therefore is just the sum of T. So the Ci's are now linear functionals and the Wi's are some vectors. So we have managed to write the given operator T as a linear combination of operators of the form T of Ci Wi. Therefore what this means is that the given operator T is actually in the image of psi tilde. This is just in its psi tilde acting on summation Ci tensor Wi. Good. So we have shown that psi is on 2. Now the isomorphism bit is now just going to be from a dimension count. Okay. So observe that we have a vector space here, a vector space here, you have an onto map between them. Now if the dimensions are equal, then that onto map must also be an isomorphism. Okay, so let's calculate the dimensions on both sides. So if you see what the dimension of Hom f VW is, that's just like, so what are these? These are linear transformations. So what's the dimension of Hom f VW? This is like, you can think of this as linear operators. This is like n cross m matrices if you wish, right, or m cross n matrices. You can identify this with all, you know, if you think of matrices with entries in F, I mean you can identify it with that F vector space, right, just by choosing bases on both sides. So what's that? Linear operators are really matrices, and matrices are, well, m cross n matrices. This have dimension mn. On the other hand, the dimension of V star tensor W, as we just did in the previous problem, is the product of the dimensions. So this is dimension of V star times the dimension of W, but the dimension of V star is the same as the dimension of V, right? So this is again nm, which means that these two dimensions are equal. Okay, and we are done, because then going back and onto map, here is an onto map and the two dimensions are equal, dimensions equal. Therefore this onto map must also be an isomorphism. Okay, so this is an important isomorphism. This gives you a very natural way of thinking about what matrices are. They are also like a tensor product. Okay, and like we said before when we talked about functors and so on, this is a natural isomorphism. That's somehow the key point here. Okay, that you can say, you can make this completely functorial and so on, but we won't, let's not bother about that right now. Let's just think of it as, given any V and W, there is such an isomorphism. Okay.